Hello and welcome to AGN 3613. In the last session we addressed how to calculate the effective rate per pay period. In this session we will go into more details addressing the discrete and continuous compounding interest, knowing that a payment period could have one or more interest periods. For example, a quarterly payment could have interest compounding monthly. That means we have 3 months within a quarter, which means we have 3 interest periods within each quarter. Considering the interest periods per payment periods, the formula will be I equal to 1 plus R, and R is the nominal interest rate, divided by C multiplied by K, and C is the number of interest period per payment, and K is the number of payment periods per year. All that to the power C minus 1. And this is the formula that we are going to use to calculate the effective interest rate. Let's look at the following example. We have 12% compounded monthly. The payment period is equal to quarter. So the effective interest rate per quarter will equal to I equal to 1 plus 0.01 to the power 3 minus 1. Why? Because we have 3 interest periods within that payment period or within that quarter, and that will equal to 3.03% rate within that payment period. So again, if you look at that, you can see that we have 1 interest period, 2 interest periods, 3 interest periods, and we don't add them. We don't add like 1 plus 1 plus 1 is equal to 3. Actually, we have to use this formula to calculate the effective per pay period per quarter. 3 is the number of interest periods here, and 0.01 is the interest per month. Having that will give us an interest rate of 3.03%. How about the effective annual interest rate? If you calculate that using the 12 months, if we look at the 12 months, then it will be 12.68% and not 12%. Now if we look at it from a different point of view, and we said, but we calculated that in quarters, so I have 0.03% per quarter. Then I have 1, 2, 3, and 4. So I can use a formula that I effective is equal to 1 plus 0.0303 to the power 4. So either I will use the 0.01 for 12 months, or I can use the 0.0303 to the power 4 because I have 4 quarters, and both should give me the same outcome or the same result. If the number of payment periods can be defined like every day, every week, every month, or every quarter, then that will be called discrete compounding. Discrete compounding, because I have certain numbers, so it's discrete, either by day, by week, by month. What if the number of interest periods approaching infinity? Then R over CK will approach almost 0. And we can approximate the continuous compounding rate to equal to the exponent raised to the power R divided by K all minus 1. And that will be our formula for the continuous. And when we say continuous, we mean that we have small interest periods to the limit that we can break it into smaller than a day. Could be hours, minutes. Every minute or every second even, we have an interest that is building, so it's building interest as we go, and that is called continuous. While if we have certain periods like day, week, month, year, or quarters, that means it's discrete. So that's the difference between the discrete and the continuous. And we have two different equations to use, one for the discrete and one for the continuous. So let's look at the following example with two cases. The first case, discrete with 8% compounding quarterly, and payment period is quarter. So the payment period is quarter and the interest period is quarter. If the nominal is 8%, then I will actually find the interest per period, or per the interest period, which is 8% divided by 4, and that will equal to 2%. Then I will use the formula I is equal to 1 plus R divided by CK to the power C minus 1. So if it's 8% divided by 4, and we know that the interest period is 1 within that payment period, multiplied by 4, so 8% divided by 4, that's 2%, and C, like we have here, is 1 minus 1, and that will be 2% per quarter. So that will be the interest per quarter, the interest per quarter. What if it was discrete compounded monthly and the payment is quarterly? So now we have 3 interest periods within that payment period. 3 interest periods within that payment period. We have 4 payment period per year, 4 quarters. We have 3 interest periods per quarter. That's 3 months per quarter. Then the total will be M, which is K multiplied by C, or CK, which will equal to 12 interest periods per year. Using the formula, then we have 8% divided by 12, and 3 is the interest periods per quarter. Then we have 2.013% per quarter. In the third case, what if we have the interest compounded weekly? Then we have 13 interest periods per payment period. We have 13 weeks within a quarter. Using the formula and plugging in the numbers, the interest per pay period or quarter will be 2.0186%. And again, we use 13 interest periods within 4 quarters per year. So 13 times 4, which is 52. So we divided the interest, nominal interest, R, by the total number of interest periods in a year, which is 52, and we raise that to the power 13 to get the interest per quarter. What if we have infinite interest periods? In this case, we use the exponent with R equal to 8% and K is equal to 4. So it will be e to the power 0.02 minus 1, all minus 1, and that will be 2.0201% per quarter. And those are the four cases as you see in the table. It's comparing the differences between the various effective interest rates with the four cases: quarterly, monthly, weekly, and continuously. And that is the difference between having interest period that is equal to payment period, or interest period is not equal to the payment period. So again, what are the steps for equivalence analysis using effective interest rates? First, we need to identify the payment period. Is it annual? Is it quarter? Is it per month? Is it week? Etc. And we identify, or we define, the period. Then the second step is to identify the interest period. For example, is it annual, quarterly, monthly? So we are first defining the payment period, then defining the interest period. And the third step is to find the effective interest rate that covers the payment period, the effective interest rate that covers the payment period. How many interest rates are there in a payment period? Based on that, we can calculate I. Let's look at some cases. What will happen when payment periods and compounding periods coincide? We will go with the process of the same steps of identifying the payment periods and the compounding interest periods. If they are the same, n is equal to m, then we use the appropriate formula, whether finding future value or present value or annuity, with the interest rate I that we found. So we calculate I first, and then we find, or we use the formula to calculate any missing value, whether future value or present value or annuity. As an example, let's calculate an auto loan payment. Assuming that you went to a car dealer, you selected a car with an invoice price of $21,599. The sales tax is 4% on $21,599. That will be equal to $863.96. Dealer's fee is 1% of the invoice price, that is $215.99, which brings the total purchase price to $22,678.95. You made a down payment of $2,679.95. So you are left with $20,000 to pay for the dealer over 48 months with an interest rate of 8.5% APR, or nominal rate, 8.5% APR. What will be the monthly payment for the car? What will be the monthly payment for the car? Subtracting the $2,678.95 from the total, you will get $20,000, which is left on the account to be paid back. R is the 8.5% per year, which is the nominal rate. Payment per year is 12 payments, 12 months, 12 payments. Number of payments for the whole, the total number of payments for the whole amount is 48 months. So you are returning the 20,000 over 48 months. The monthly interest will equal to 8.5% divided by 12, which is equal to 0.7083% per month. Based on that, we use the equation or the formula A equal to the principal P, which is 20,000, multiplied by the factor A given P. It's not divided. This is not division. This is not a division sign. This is A given P with 0.7083% and 48 periods. 48 periods. If you can find that in the book, which is going to be hard because we don't have the 0.7083% in the back of the book, so you can actually use the calculations or the mathematical calculations, the formula that we give for annuity, and then you can find the annuity based on the given information, and you should have $492.97. Now, suppose that you want to pay off the remaining loan in a lump sum right after making the 25th payment. How much would this payoff amount be? So your annuity, your monthly payment is $492.97. After 25 payments from the 48, 25 from 48, you decided that you would like to pay off the whole amount. So you have 23 payments left. 23 payments left. How much would you pay? To show you exactly how this will work, let's calculate that. So we have the payments. We already borrowed $20,000, and that what was borrowed on the car, and we made the payments of $492.97, and we did that for 25 payments. So now we're done on number 25, and then up to 48. This is number 48. So from 26 to 48, this is what we would like to pay. This is what we would like to pay. So this one has been paid already, and I would like to pay this amount. So to do that, what we are going to do, we're going to ignore the first part because it has been done, and start from 26. So this is 26, and then we have 27, 28, all the way up to period number 48, and those are 23 periods, 23 payments that is left outstanding. Now remember that we found that I is equal to 0.7083%. So I will consider this as a present value because already I'm done with those payments. So this will be my present value over here. And based on that, I will bring all these annuities back to the present value. So my equation will be P with A, where P given A, and again I said that this is not a division, it's called given. So P given A and 0.7083% interest, and number of period is 23, and this is called the factor. It's a present value factor or present worth factor. So this is the factor that you find on the back of the book, but since we don't have this value in the back of the book, exact value in the back of the book, you can use the mathematical calculation. So if you do that, and A is $4.92.97 multiplied by the factor, and the factor here is 21.1556. So if you multiply that one with the amount, which is $492.97, you will get $10,428.96, and this is the amount that you need to pay now after paying 25 payments. So to own the car and to get rid of the payments, the 23 payments that is left on the account, you need to pay this amount here. Now let's take another example. If you smoke, or you know someone that smokes, you might be interested in this example. This example actually calculates the amount of savings that someone might have if they save the cost of the pack of cigarettes in a bank instead of buying one, and that will be over 50 years with an account that provides interest rate of 5.5%, an annual interest rate of 5.5%. So the tables here actually shows 3 levels of smokers. The one who smokes 1 pack a day with 5.5% interest can save up to $169,325. The level 2 with 2 packs a day will save up to $339,650. The level 3 packs a day will save up to $507,976. By the way, all these calculations have been done assuming that the value of the pack is $1.75, while the actual value of the pack between $4 and $11 these days. So imagine how much would you be saving if deposited these amounts in the bank. To confirm the numbers, you can go over the calculations yourself. This slide actually shows the example of 1 pack at $1.75 per pack. Since the interest is compounded weekly, then I is equal to 5.5% divided by 13 times 4. We have 13 weeks per period per quarter times 4 quarters, or you can say that we have 52 weeks per year. So you have interest of 0.10577% per week. Now let's compute the equivalence value with a weekly deposit amount of $1.75 multiplied by 7. So the weekly deposited amount should be $12.25 per week, with $1.75 per day, 7 days a week. That's $12.25 per week. Now the total number of deposited period, we have 52 weeks per year, but over 50 years. So multiply the 52 by 50, you will get N, which is the number of deposit periods or payment periods, and that will be 2600 weeks. So with interest rate of 0.10577% and 2600 periods or deposits with $12.25 a deposit, you will get a future value of $169,325. This is how much would you save if you smoke one pack, that the value of it only $1.75. So imagine how much would you save. Actually, I want you to try and use the actual price for today's cigarette to calculate how much savings would you make if you deposit that amount in the bank. And let's assume that the interest is just 5.5% compounded weekly. Just add that or calculate that and see how much money you will be saving by the time you retire. Whether you are near retirement or not, just calculate that and see how much will be by the time you are 65 years old. How much would you save in the bank? Another example is the savings that you can make if you stop drinking coffee and saved a $2 cost of a cup in your bank account. And you can do the calculations over 30 years with an interest rate of 5% compounded daily, because you drink the coffee daily. Assuming that you will drink 1 cup a day, you will find that these calculations, dividing the 5% nominal rate by 365, you will get the effective rate per day, which is 0.0137%. And since I'm considering 30 years, then the number of periods will be 30 times 365, which is 10,950 days within these 30 years. With the interest of 0.0137% and a deposit of $2 per day, I will get $50,831 over 30 years. This is how much I would be saving if I stopped the coffee. So stop the coffee, stop the smoking, and deposit that in an account, and by the time you retire, actually you will have a decent amount to use it after retirement in your saving account. In the second case, when payment period differ from compounding periods, we go through the first step, which is identifying the M, K, and C. Then we compute the effective interest rate. If discrete, we use the formula I is equal to 1 plus R divided by CK to the power C minus 1. If continuous, we use the formula I is equal to the exponent to the power R divided by K, all minus 1. Then we find N, and we use the appropriate equivalence formula with proper I and proper N. So first we find I, then we find N, and then we use the formula whether I'm calculating the future value, the present value, or the annuity. We use the new I, the effective I, and the number of periods N. This example addresses a discrete case with monthly compounding rate, assuming that R is equal to 12%, then I will equal to 3.03% per quarter, and we have 4 quarters or payments periods per year. For 3 years, then it will be 4 times 3, which is equal to 12 payment period. Using the formula, then the future value with $1,000 payment per quarter, it will equal to $14,216, and 24 cents. If it was continuous, we use the exponential formula, and I will equal to at that point will equal to 3.045% with n still 12%, 12 periods. Then we have a future value that will equal to $14,228.37. Let's take another example, and in this one we are trying to find the present value or principal value if we made equal payments of $5,000 quarterly for the next 10 years with interest rate of 9% compounded. The first option or the first question will be when it's quarterly, the second question will be when it's monthly, and the third one when it's continuously. So we have three parts of the question, and we will solve each part separately. So let's start with the first part, when it's quarterly. What does it mean quarterly? It means that I have a payment period that is equal to quarter, and the interest period is equal to quarter. That means that I, effective I, is just equal to the nominal 9% rate divided by 4, which is equal to 2.25% per quarter. And over 10 years, we have 4 quarters per year multiplied by 10, that's 40 quarters or 40 payment periods. So the present value will equal to the annuity, which is 5,000, multiplied by the factor, which is P given A, with 2.25% and 40 payment periods. And that will equal to $130,968. If it's monthly, then we have 3 interest periods within the quarter. So first I have to divide the 9% divided by 12, and I will get the monthly percentage, which is 0.75%. Then I will use the formula, and I will find I effective, which will equal to 1 plus the 0.75% all to the power 3 minus 1. And that will equal to 2.267% per quarter. Again, the number n here did not change because I have 4 quarters per year and I have 10 years, so I have n equal to 40 quarters or 40 payment periods. Based on that, P will equal to A, which is 5,000, multiplied by the factor. Now with a new interest rate, which is 2.267% and 40 payment periods. The overall present value will equal to $130,586. $130,586. The third part of the question, when it's continuous. And continuous, we use the exponent. So I is equal to the exponent to the power 0.09 divided by 4, all minus 1, and that will equal to 2.276% per quarter. N is still 40. Using the formula, then P will equal to $130,384, and that will be the P when it's continuous. And as you notice, we have the interest rate is changing, and based on the new effective interest rate, the P value is changing, or the present value is changing. That will be all for this session. If you have any questions, you can use any of the communication channel to send it or communicate with me. Thank you and have a great day.